We talked about hashes because hashes are great and hashes let you do everything. And if they're sponges, they're even better and you can do even more things. But that's not how cryptography started. I like to start from hashes because that's the thing we use for a bit of everything. But we definitely started with block ciphers. And there is a very good chapter on block ciphers in the book. I wanted to pull up the diagram here. And it has a detailed explanation. It breaks down how they work internally and how generally the symmetric magic box works. I have found I needed to understand that precisely 0 times in my career because they work. Those are one of those, while things like Merkle-Damgard, you do need to understand how it works because then, boom, length extension, attacks, stuff like that. AES has been around my entire career, which is the block cipher specified by NIST, the Advanced Encryption Standard, to competition, which I think was maybe was the first time that they ran a competition, and there were a number of submissions, Serpent, Regindale, and they picked Regindale to become the AES, the Advanced Encryption Standard. And AES works. I think it lost 2 bits of security to cryptanalysis in 25 years, 30 years. How long has Regindale been around? Probably longer. I tend not to update in my head how old something is as years pass. But yes.
It's not complicated to answer. How do you measure that you lost 2 bits of security?
Question is, how do you measure you lost 2 bits of security? It means that there's somewhere in a paper a theoretical attack that you can run against the cipher, for example, against AES-128 to recover the key or break a ciphertext in 2 to the 126 work. Now, nobody can count 2 to 126, just like nobody can count 2 to 128. But it's how we measure. Wikipedia has varying quality on cryptography topics, but one thing I find pretty always on point is at the bottom of the info box, there's always a best public cryptanalysis, which I found is almost always up to date. And so I use that generally to check if my information is up to date on this stuff. And here it tells us that, it lost 2 bits. And the AES-256 lost also 2 bits. And then there's a related key attack, which works only against 192 and 256. So useful thing. Okay, so block cipher is the thing where you give it a fixed size key, a fixed size input plaintext. You get a output ciphertext of the same size of the plaintext, and then you have the inverse function, which we basically never use these days. We'll see why. To go back from the ciphertext to the plaintext, still using the key. So it's a family of permutations selected by the key, and the properties are that from the ciphertext you can't recover the key, you can't recover the plaintext better than brute forcing the key. Okay. Related key attacks. Related key attacks are attacks where there is a strong relation between the keys, like 2 keys differ by a single bit or something like that. In theory, in the ideal model, even if your keys are just like different by a single bit, in theory that should diffuse to the entire ciphertext, and the confusion should be deep enough. We'll see what these 2 terms are, but it should be such that it doesn't really matter, doesn't change anything. But in practice, it does make the cipher weaker. But the thing is, nobody does related keys. Why are you doing related keys? We have key derivation functions. Just derive 2 keys from a single key. Why are you? So generally speaking, related key attacks are academic in value, and Yeah, when somebody goes like, oh no, but the related key attacks apply to us, you stop, you sit them down, you ask them, what the hell have you been doing? Because that's just bad cryptography engineering if you do suffer from related key attacks. It's curious that the related key attack applies to AS256 and 192 and not to 128. So we're looking at block ciphers, which are the functions where you have a fixed size ciphertext, fixed size plain text in, fixed size ciphertext out, and the key selects which permutation will be used. So how AS works is that you generally need to do two things in a block cipher. Well, three things. You need to mix in the key somehow at each round. You need to shuffle stuff around, and you need to do some substitution. So substitution is very much what you would think, like a table. If you have this byte, you put this other byte, and it's a fixed table. These are called S boxes. AS is essentially the only block cipher you're going to encounter in actual production anywhere these days, and partially because it works, it's secure, nobody has any doubt about its security, and because these days it's implemented in hardware in most of the chips you will encounter. When it was starting 10 years ago, you would have to think, well, but the phones, they don't have hardware to do AES, so they have to do it in software, which is lower, which consumes more battery, so we should have a fallback that's more friendly to the phones. All phones have AES these days, so AES is fine. How AES works, you give it a key, you give it a plain text, out comes a ciphertext. What it does is first it takes the key and expands it with a thing called a key schedule. That's not quite the same thing as a key derivation function. A key schedule does not have to make completely independent keys. It just has to make it such the rounds. Each round does not do the exact same thing, because if it did the exact same thing, you could slide the intermediate inputs to the rounds and get and do attacks like that, which is you'll see a pattern. How we attack Merkle-Dangard, we take the intermediate state, we take the output state, and we put it back in as an intermediate state. Same with slide attacks against block ciphers. Anyway, it takes a key, the key schedule expands it into a key for each round. AES has 12 rounds, I think. Well, it has 12 rounds in the 128-bit case. So it expands the key to those 12 keys, and then it does 12 times the same thing, which is what the diagram is there. It adds the round key, then it moves things around. So it mixes columns, it shifts rows, which is just taking things and moving them around. And then it does substitution, where each byte gets replaced with a different byte from a table, which is a fixed table called S box. And S boxes have to be as non-linear as possible. There needs to not be a simple equation that describes the inputs and the outputs. Because if you have that, then you can do linear algebra to it, and then you can describe the whole thing through, and you can reverse it. And it just does that a few times. And the mixing things around helps with diffusion. So if you change one bit over here, in a few rounds, it will change everything else, because one bit there will then get mixed, cause the byte to get substituted over there, which then will get mixed somewhere else and will cause another byte to get substituted, and that keeps avalanching. I think AES reaches total diffusion in 4 rounds. Don't quote me on that. But after a certain number of rounds, you get the situation where every bit in the state depends on every bit in the state n rounds before. That's diffusion, when where the effect of one bit changing changes everything else. And then there's confusion, which is about how hard it is to track how changes progress through a column of bits. There is a lot to say about this stuff, and it's not even particularly my field. These days, there is very little excitement about how to build block ciphers and how to do them, because I mean, AES succeeded. It's good enough. And second, it's now enshrined in hardware. So all of the interesting new stuff that's happening is reusing the AES hardware to maybe do something a little different at the edges. There's stuff like Aegis, which is interesting authenticated cipher that uses the AES core. But at this point, making a block cipher not using the AES core makes no sense. Anyway, the book has a bunch of stuff on this, partially because the author has designed block ciphers, has designed a low-level symmetric crypto. So it's very interesting, not particularly practical for us. So let's assume that the box is magic. The box is magic. There, we have a magic little box that takes a key, takes a plain text in, and gives us a ciphertext out, or vice versa. Good. How do we do things with that? Just like the other lesson, we looked at how we could go up from block cipher to compression function, from compression function to hash function, from hash function to MAC, from MAC to KDF. Here we take the block cipher and we go up to, again, authenticated encryption. Why authenticated encryption? I guess we can see it by looking at one of the modes. All right. Ideas for how we encrypt a large message given the magic box that takes a fixed size input. Go.
We divide it in chunks and we
encrypt each chunk. Yep. We do that. And then we do that with an image. And what happens is that the image looks like this. Why? This is the ECB penguin. It's such a good visualization of the issue.
Blocks and keyboard blocks.
Exactly. Every time the color is the same, the output is the input bytes are the same, the output bytes are the same, and you can tell because you just the encryption is deterministic. The box does not bring in randomness.
Because I thought that like the key for every block was different.
No, we have a magic box which takes a key, and the key gets expanded for different rounds, but that's inside the box.
Okay, the key gets expanded inside the round, not on the sequence of blocks.
Exactly.
Okay,
Exactly.
I thought the key would be expanded.
The key schedule thing we mentioned is a thing that's inside the box of the block cipher, which is just how block ciphers are implemented generally. They're implemented by having a key schedule that expands for rounds, running a certain number of rounds of that sequence of operations, which are adding the key, the round key, and but all of those things I mentioned because I mean it's kind of nice to know how things work in practice, not to think about them as completely magic, but then we can immediately close the box, consider it magic. But now we have one key, because that's our key, the 128 bits.
But I guess you can generate other keys with the key generator.
One thing you could do is that you have a key derivation function, you could just derive a different key for every block. Yes, horribly slow. Because a key derivation function is reasonably fast, but not like there are a lot of blocks. A block is AES operates on 128-bit blocks. These days, you will not find anything smaller than that. Older ciphers like DES did work on smaller blocks. If we have time, we're going to talk about how that has combinatorics problems because 2 to the 64 is not a particularly large number. And so you can do just combinatorics things without even looking inside the box. But in general, it's 128 bits. But 128 bits is not a lot. And so you end up with a lot of blocks. And deriving a new key every time is going to take forever. Also, AES has performance cost every time you start using a new key because you have to do that key schedule. So if you can pre-compute the key schedule and then use it for multiple blocks, you're going to be faster. So we can't just chop it up and do that. Other ideas? It's always a damn counter. It's always a counter. Do you see a pattern? How we do cryptography is that we basically always stick a counter in there and see what happens. Okay, so with countering, we exactly do that. And can we just use a counter? Well, yes, if we are encrypting a single message, like a single image. If we want to encrypt multiple things with the same key, we're going to need two things, a counter and a nonce. And so you can build so many things with nonce, which is so you will find debates on the nomenclature to use here. I like to use nonce when it just has to not repeat. So you could use, again, a counter, like a value that you never use twice and once. And I use IV when it has to have other properties, like being unpredictable, uniformly random, secret, things like that. Well, IVs usually are not secret, but for this, you just need a nonce. You just need a value that is different for each message and a counter that is different for each block. When I say message, I mean like an image. You're encrypting 10 images. Those are 10 messages, and each of them will be made of a number of blocks. So what we do is we take our number used once, concatenate it with a counter. Remember that we only have 128 bits of space, so we have to make sure that that everything fits. We encrypt it with the block cipher and the fixed key. What comes out is random bits as far as the attacker is concerned, right? Because unless they know the key, even if they know the number used once on the counter, they can't figure out what these output bits in ciphertext are. And then we XOR, because that's the other tool that we use for everything in symmetric cryptography. Outcomes unpredictable bits, great. Now you XOR. And if you squint, that's a one-time hack. The key stream that comes out of encrypting those, so the key stream that comes here and here and here, you put it all in a row, it's just a long, not infinite, the counter runs out and there are other things that happen at some point. But it's a long sequence of random bits. And if you have a long sequence of random bits and something you want to hide, what do? You XOR them, and the result is as unpredictable as the cipher string. And if you want to decrypt, what do? Exact same thing, because one-time pad is just you just XOR again, and XOR takes out. We talked about XOR in the first lesson, if you remember, and XOR is simply, if it's 1, you change the bit. If it's 0, you leave the bit alone. And if you XOR twice by the same thing, you go back to where you started always. 0, 0, nothing, nothing. 1, 1, flip, and then flip again, and you're back to where you started. Cool, okay, so essentially what we did is we built a stream of bits, so a stream cipher out of a block cipher, and that's what CTR does.
2 questions. One, here you need to send the nonce.
Yes. You have to, the recipient needs to know the nonce. There are different ways the recipient can know the nonce. One option is you send it together. That's totally reasonable. You put it at the beginning of the encrypted message, and that's how they know it. Another one is that maybe you're using a key derivation function to make the key. Pull the nonce out of the key derivation function too. It actually provides some nice combinatorics properties if you do that, because then the nonce is also unpredictable, and it helps with multi-target attacks. We can talk about those in a minute.
But if you want to send many images, you need different nonces, so you need to agree on how.
Yeah. I mean, one option is that you have a main key, and for every image, you derive a key from, I don't know, the file name or by using the key derivation functions using hackers that we discussed earlier, and you derive both key and nonce and at once, and you use the key only once and the nonce only once. So you technically don't have to derive a random nonce, but why not? It helps. Might as well. Yeah, that's generally useful pattern. TLS does that, for example. TLS does a bunch of key schedule stuff from asymmetric and cryptography stuff, and then it pulls out key and nonce at the same time and uses that. Okay, yes.
Can I go back like a couple of pixels? Go.
Yep.
Here, if you do the XOR with the plain text before the cipher, is there anything wrong with that? So the plain text enters.
Oh, I see.
The...
I think that might actually have a name. So the nice thing about doing it this way is that you are first turning the block cipher into a string, and then using a string cipher. And the string cipher is just a generalization of the concept of the one-time pad, where, however, you don't actually distribute the entire key string, but you have a way to derive the key string from a key. And that's generally nice because we have other string ciphers, and then we can just, turn thing into string cipher and then reason about that. And there are other block modes. We will skim them. In practice, these days you use this, and you turn to string cipher. I think it has a name, and it's probably on this page somewhere. You don't use. It's not one of the common ones, but I'm pretty sure it exists. This one, no. I can look it up. Anyway, there are so many block modes because this was early days of cryptography. People were trying out stuff. They're trying to figure out how to make it work and so on. The other one that you're likely to encounter is CVC, which is this one. In this one, you have an initialization vector, which is that has to be random and uniformly so. And messing that up opens the door to so many attacks. You XOR that with the plain text. The out comes the ciphertext directly from the block cipher, and then you XOR the ciphertext with the next block of plain text. It becomes the IP for the next step. And the attacks here usually look like, as usual, taking an intermediate state and putting it back in as a starting state. Because if you swing, you can remove. Bring this down a bit. You can remove this part, and now it looks the same, right? This is now the IP for that part, and so you can chop things up, and it will work. Which I mean, this is not authenticated. That's to be expected, but you can do similar things. Or okay, so actually, let's do the exercise first with CTR. This will protect confidentiality, but if I want to change the plain text here, and let's look at decryption. Oh, another useful thing about CTR, you only need encryption, because to both encryption of the block node, because to both encrypt and decrypt, what you do is you encrypt the counter and then XOR. You just you separate into generate key stream, and you do that by encrypting the counters and using the key stream, which will be XOR both on the way in and on the way out. Which means that you don't have to write the code for the decryption function of AES, which is nice because maybe you don't have space for that or along those lines. But let's say that you want to change the letter that's here. You think it's a 0, and you want to turn it into a 1, because you think that that's where the system stores whether you are administrator or not. Can you? Like you control the ciphertext, because this is the situation where I encrypted something, put it on a USB drive, gave it to him to bring to you, and he can change things in that USB drive. He can't read the message because it's encrypted with this, but he can tamper with it. How do you change this from 0 to 1.
If they put it,
You flip this bit. If you flip this bit, what happens to this one? It's XOR. It propagates. So if you just XOR this with any byte, this will get XORed with those bytes. If you know what was in here, or you have a guess, you can XOR this with your guess, and what does this become? 0, because it will become what it used to be, XOR your guess of what it used to be. If you XOR something with itself, it comes out to 0, because 0 and 0 XOR to 0, 1 and 1 XOR to 0. And then you can XOR it again with whatever you want, and now outcome, this becomes whatever you want. You can tamper with these. These are not authenticated. All of these modes only protect confidentiality. They don't protect integrity, and they don't provide authentication. This leads to so many attacks when developers do cryptography and just hand roll things because they don't think about that. This is also true of CVC. You can also do a similar thing with CVC. And there are actually very fun attacks to do with CVC, like very, very fun attacks. If you want to change, sorry, decryption. If you want to change this bit here, you just change a bit here. You have to realize that this will make this become garbage, because if you change a single bit here, this will change all of the bits in its output. And so this will come out to just garbage. But this will become what you just wanted it to become. Anyway, they all have different failure modes. Yes.
In CVC, the receiver needs the initialization vector, right?
Yes.
So why don't you use some sort of like nonce?
So the initialization vector, you prepend it usually to the ciphertext, just like with the nonce. And you select it at random when you encrypt. You just go to a random number generator, the one from your operating system, and you ask 128 random bits, please.
But the role of the initialization vector and the role of the nonce is basically the same.
Basically the same. The difference is that the nonce can just be a counter because it just has to be a non-repeating. The initialization vector can't be just a counter because imagine you use 1 and then 2. Let's look at encryption. Imagine you use 1. What was the attack? Hold on, I'm blanking. I think it's in the chosen. Yes, it leads to a chosen plain text attack. If you can predict what the IV is going to be, remember the games we talked about in the first lessons.
The device and
no, the games, the ones where you give the attacker the ability to submit plain text and get ciphertext, and you challenge them to distinguish the output. You can build a very simple distinguisher because if you know what the next initialization vector is going to be, you can put the first block of the plain text to be the same. What will XOR here? If this and this are the same. 0. And so this will encrypt 0, and this will be the encryption of 0. And then you just do that twice, and it comes out to 0, to the same thing twice, and then you go like, that one. That one is the encrypted one, and you've distinguished it from random. So this has to be unpredictable and uniformly random, which is not true of nonces. Nonces can be just a counter that's predictable and so on.
because the thing that I don't understand is like the attacker knows the initialization vector, right?
They know it after the fact. They don't know it when they are choosing the plain text. That's why I'm saying unpredictable and not secret. Secret means they never learn it. Unpredictable means they can't know it in advance when they're preparing their plaintext. Every time you run a CBC encryption, it comes out with a completely new unpredictable IV, so you can't predict what to put in here in order to get this to do something that you want. And after it's done, too late. Anyway, CBC, not, I mean, kind of in production, but not that much. Partially also because string ciphers, you don't have the problem of what if my message is yay long? You just stop XORing at that point. So CBC, you actually have to put things inside the block cipher. So you have to come up with padding. And then from padding, you can do padding oracles, which are extremely fun and hopefully not a thing that you'll encounter that much because hopefully most of the time you're just going to be doing CTR and I want to get to authenticated encryption. We have a break in a minute, so I will talk about oracles, but let's use CTR for oracles instead, because when oracle attacks are taught, they're usually taught focusing only on the block cipher because that's convenient because you're analyzing a single chunk of but usually you use the stuff inside a larger application, right? Larger applications have oracles all the time. That's why you need authentication at a lower layer. Oracle is just, so these things guarantee that without a key, the attacker can't decrypt the thing by just looking at it. Great. But there is someone who has the key, right? The recipient. And the recipient is probably a computer connected to the internet that does something with it. Otherwise, it's kind of not a very useful cryptography system if it does not involve a thing that actually receives the thing and decrypts it and does things with it. So oracles are when you send the encrypted message and you just check what happens. If the time I take to decrypt something depends on the encrypted message, you can measure that and use that side channel. Oracle can be any kind of side channels. For example, imagine that there's a situation where if the last few bytes of the ciphertext, the last byte, let's say, is in my parser, it can't be at 0. A message cannot end with 0. So if it's the last byte of the ciphertext is 0, I just I return an error immediately. If it's not 0, instead I keep parsing it as JSON or something like that. Like I do something else.
The plaintext or the ciphertext?
The plaintext, sorry. My computer receives an encrypted message, decrypts it. If the last byte is 0, error. How do you use that to decrypt the message? Well, you use decrypt 1 byte from message. So look at decryption. And remember that we said we can tamper with it. So we just said that if this is 0, we get an error from the application because messages can't end in 0. Who knows? It's some numeric data that does not make sense for it to have 0 yet. If we have a guess about the actual plaintext, how do we verify that guess? We think the plaintext might end in 55. What do we do? So I control the ciphertext, right? Because I'm intercepting it because that's why it's being encrypted. It's going over some channel that's not trusted. So I XOR this byte with 55. What does this byte come out to? If it was actually 55 originally? 0. And what happens? I get an error. And I observe the error. And I say, I was right. If instead the byte was something else, I don't get an error. It maybe does the computation and the computation comes out wrong or something, but I get a different result. So I've just validated my guess. And I can just guess all of them if I can try enough of them. I can say, I wonder if it's 0. I send it. Well, it's not 0 because, of course, then goes an error. Maybe it's 1. I XOR it with 1. I send it. I check if I get an error. Maybe it's 2. I XOR with 2. I send it. I check if I get an error. And I keep doing it. And at the end, I will get one guess right, and that will tell me, yeah, great, that's the last byte of the plain test, and that's an oracle attack. There are endless variety of ways you can build oracles out of applications. Applications cannot be trusted to behave always the same based on different inputs for a myriad of reasons. So what you need to do is authenticate the ciphertext, which we can look at after the break. Does this make sense though? Like why oracles are a problem? Cool. Questions before the break? No? All right. Sounds like you have questions. Go for it. What were you thinking through?
Okay, yeah, what the reason was like, so you mentioned there are problems with authentications even prior to the hypothesis that the software will crash into zero or something like that. And so we're trying to understand what kind of problems you could have more specifically.
Yep.
So like we were thinking of examples, and like one thing, perhaps I'll say to see if it's correct. So if you, so say you see a conversation and like you think you have a good guess for what they said, say you're able to, you have control of the communication channel.
Yep.
Then if they send a message, you expect to know what they said.
Yep.
Okay, so with that, then you get, and then if you like put the message away and substitute it with
anything you want.
Yep. You can substitute the message.
Yep.
So that's the kind of problem you were.
Exactly.
Oh.
Yeah, you can have these are completely unauthenticated. You have complete control based on any guess that you may have. If you have a guess as to the words, you XOR them out, and then you XOR in whatever you want. This works with any stream cipher. So yeah,
but the principle is that, but you have to like throw away the original message because like if the message goes through, then the nonce is burned, and so the thing that is useless. Right?
The receiving side usually does not is not stateless. Is not stateful. Like usually the receiving side will not keep a giant table of all of the nonces that were used. The sending side has to never use a nonce, so it needs to have a good story for why the nonces are not repeating. The receiving side sometimes has synchronized nonces where it will like the nonce is a counter and it will then keep moving it forward, so you only get one shot. But it's absolutely as possible that the nonce is at the beginning of the message, and you can keep using the same nonce for as many times as you want.
So I all in one nonce,
you might be able to keep sending new messages that all get accepted and break authentication multiple times, depending on how the nonce is derived. There is no authentication here at all. And this is true of any stream cipher. So if you cut here, where the things that come out of the encryption are your key stream, then you can substitute an actual stream cipher like Cha-Cha or Salsa, which instead of having a block cipher that with a key that encrypts, what they have is a permutation. Again, and you compose a state from some constants at the top, the key, which is 256 bits for Cha-Cha, some counter blocks, but this is Bernstein's version, so let's go down to the standard one. A counter, and then the nonce, and then you run a permutation on this. And since a secure permutation will make it so every bit of the output depends on every bit of the input, but if you change even a single bit, there will be no statistical relation, detectable relation between the two things. You can just keep flipping this counter, run the permutation, and generate the key string. Just like earlier, we were using the in CTR, we were using the block cipher to encrypt counter and nonce with the key, which are just two separate inputs. Here we have a single input to the permutation. We structure it with both the key, the counter, and the nonce. We keep running it, and we keep churning out key string. And then we use that for XORing. Basically the same mechanism, except instead of using a little box with two arrows in and one arrow out, we are using a little box with one arrow in and one arrow out. of the same size. And it's just a little nicer to reason about because it's also a very reusable tool, that permutation, because see yesterday, you can build sponges with it. Anyway. Right. The differences between these two is kind of inconsequential. This Cha-Cha is a little easier to implement in software. AES is a little easier to implement in hardware. Most hardware has AES support these days, so there are fewer and fewer reasons to use Cha-Cha anywhere. Anyway, doesn't matter if you use CTR, AES CTR, or Cha-Cha 20. The problem is you have no authentication. So how do you do authentication? You compose it. And you can either actually compose it in two separate modes. So you can use, for example, the hashes from yesterday to do authentication. Or you can use a pre-made composition, which I wonder if we have a diagram of. Yes, there we go. Well, that helped. And authentication is the concept that using a key, you produce another value, the MAC, the message authentication code, such that you need to know the key to make a valid MAC for a message. And usually what you do is you authenticate the ciphertext. This way, before you even decrypt it, you know that only somebody who knows the key could have made that. And then all of your authentication problems go away, because if anything was changed in the ciphertext, then the MAC does not match, and so you stop and you return an error before leaking any information. It actually took a minute to realize that you need to authenticate the ciphertext and not the plain text. Why? Well, Zuko put it beautifully in the cryptographic doom principle. If you do anything before authenticating, you're doomed. So if you apply any computation, run any processing before you've authenticated what you received, and processing that involves the secret key, there are probably going to be side channels like error oracles, timing oracles, and things like that will lead to leaking the cipher, the plaintext. But if instead you do the reasonable thing and you take the ciphertext, you authenticate that first. So, and when you decrypt, the first thing you do is you take your key, your authentication key, you use two separate keys. You run the authentication over the whole ciphertext. It comes out a message authentication code. You compare it with the one that's attached to the ciphertext. Usually we put that at the end. Generally, we put the nonce at the beginning, the MAC at the end. It's not mandatory, but like generally you need to know the nonce to start processing stuff. So you need it before. And the MAC is only useful once you're done, because you authenticate things as you receive them. These are implementation considerations. Sometimes the message is large, so you want to process it as it comes in and makes things a little faster. But one useful thing about CTR and Cha-Cha, by the way, you can run them in parallel. You can generate multiple chunks of the key stream at the same time, because you can just encrypt multiple counters at once. And you can either do that using multiple processors in your machine, because your machine usually has more than one processor. So you can say, all right, you encrypt with 1, you encrypt with 2, you encrypt with 3, you encrypt with 4. And then they all encrypt. You take all of the things and then you XOR all at once. That's faster than doing in sequence. Or processors these days have instructions to run things in parallel, to apply the same thing to multiple registers. Or these days, CPUs are also good at out-of-order operation. So you can make things go faster by telling the CPU, hey, do that. And after do that with a different input, as long as they don't depend on each other, and then do that, and then do that. And the microcode inside the CPU will see that they are independent of each other. They don't. The second operation does not use the output of the first operation, and we'll just schedule them in parallel so that it can, for example, amortize the time it takes to go to the RAM and back. Anyway, that's a deep dive into implementation considerations. But generally, a useful general rule is if you can do things in parallel, things are going to be faster, either because you actually do them in parallel or because CPUs these days are pretty good at doing out-of-order execution and parallel dispatch. Anyway, back to us, authentication. So how do we do authentication? Well, we can do it with hashes. We've seen that yesterday. Or there are specific functions that do that. Generally, that support that with a one-time key, and those are things like ghash, poly 1305. They're usually polynomial or Galois multiplication operations, where essentially they accumulate the message in such a way that every bit of the output again will not every bit, but yeah, in such a way that there's no way to produce an authentication code for something that you did not without having the key that's associated with it. Since these are usually one-time use, so the key has to be used once, we combine them in things like this, which is GCM and is getting cut off. So this is Galois counter mode. Galois counter mode is just a way to combine counter mode, which we've just seen, and at the top is counter mode. So up to here, you already know it, right? If you squint, it's just ignore this part. So ignoring this for now, and anything below here. This part is just counter mode that you've seen before. Make sense? This is encryption, so you just encrypt 1, encrypt 2, and then what comes out, you XOR it, and this is the ciphertext. That's just counter mode. But also, you take the ciphertext and you do the Galois multiplication of the this you can think about it as a 0, like you start at 0. We'll see in a second that you don't necessarily do that, but and then you multiply and you get that. You multiply with the ciphertext, you get that. Then you multiply with the length of the ciphertext, so that you're also authenticating how long the ciphertext was, and you get this value. This is the message authentication code. The last thing you do is that you XOR it with an encryption of counter 0. So essentially, you encrypt it. You encrypt it because if the attacker can see 2 of these, it can do linear algebra and get the key out. Sorry, the key out. It can do the linear algebra and compute any values it wants. So you encrypt it with just counter 0, which we just saved at the beginning here. The final result is that you have ciphertext, and tag at the end. Now you can't change anything, because if you change 1 bit here, this value will come out different. 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 And since this one is different, and you don't have a way to make it, to fix it without knowing the key over here, then when you send the message, the first thing the recipient will say is, nope, and toss it out. Does this make sense? Why this fixes the tag? Yes.
You mentioned Galois.
Yes. So, I don't have off the top of my head the exact internals. I think it's a polynomial of degree 128 of a binary. Damn it. I've implemented this many times, but we implemented with the few instructions that are dedicated to doing that. And so I think it's a polynomial operation where addition is XOR of the values, because abstractly it's a polynomial where coefficients are 0 or 1. That I think not my specialization, and in implementation it boils all the way down to XOR most of the time, so don't have to think about it too often.
So I'm trying to look it up.
Yep.
Maybe it's like multiplication in a finite field.
It is, yes.
In F2,
In F2, that I think that's right.
Like F2 to the n.
Yes.
In F2 to the n.
In this case, F2 to the 128.
Because for multiplication in a Galois field, that would justify the name.
Well, yes. Yeah. Honestly, I have a friend that has a very quick intuition for all of the math of it, and he can always like when things break and implementations do wrong things, he can always like pull out a different value, and I usually just rely on him for attacks. And I know enough to tell, oh, that's gonna be broken, and then I call Sean, and Sean goes like, yeah, hold on, writes 10 lines of Sage, and out comes about the authentication, but it's great. But yes, the point is that you accumulate the ciphertext values into this value, and then you encrypt it with the block 0 that you saved when you started off the key string, and you apply that at the end. Makes sense why this prevents Oracle attacks and any authentication attack?
I'm still struggling to understand what's the property of multiplication that we want.
The property of multiplication in the finite field.
Yes. So why are we using that?
I mean, this is the part where my math, that lack of math background shows. So I think both this and poly 1305, which uses a different polynomial to do the same thing, I think you can show that they are, what's the term? Perfect. There's a name. Polynomial multiplication, blah, blah, blah. I think there's a name for also for the category that I am blanking out, but the point is that I think you can show mathematically that there is that given a single use key or given you encrypt the tag, which are essentially the two similar ways to use the same things. Either you randomize this or you randomize the output. You can show that you can do a mathematical proof that there's no way for that adder to produce counterfeit ones. And that's partially why I don't understand it. When the math tells me this is provable mathematically, I go like, I believe you. And I specialize in everything that breaks after that. And poly 1305 is essentially the same thing, except instead of encrypting at the end here, you have a single use key. And how do you get that single use key? You encrypt 0, the 0 counter at the start, and you use that as the poly 1305 key. So the idea of these authentication modes is that they combine encryption and authentication by using the first, the counter 0, not to encrypt actual plaintext, but to either derive the key or encrypt the authentication code. Then they run authentication and encryption on the whole thing, and then at the end you have the authentication code that guarantees that there was no tampering with the ciphertext. I'm sorry, I can't offer the specific math justification, but assuming that the authentication code has the property that you can't produce this without knowing the without knowing multiple of these unencrypted tags, then the rest makes sense, right? Because now anything you change cascades into a change of this, and your message gets rejected. Now, GCM has an important weakness. If you use the same, here it's called an AV, but that's the nonce. If you use the same nonce twice, what happens? Counter zero, the encryption of counter zero is the same twice. It's the same twice, so you can XOR it out of the two authentication codes. You get the XOR of two authentication codes. And then you just HMAP two of these. These are called a G hash because of Galois hash. You XOR two of them together, and basically you can then produce G hashes for anything you want. So essentially, it has a catastrophic failure mode for nonce reuse. Before, if you reused a nonce, you could compromise the two messages that were encrypted with it. But here, if you reuse the nonce even once, you can then forge authentication codes under that key forever. That happens. That absolutely happens. And let's think about for a second how that happens. So nonces, we've said this diagram doesn't. I'm not a big fan of this diagram. I should make another one, but let's go back to CTR. Again, this is essentially the same. There's a little variation between the CTR mode of GCM and the CTR mode of just the standard CTR, just to make us have to implement them separately. I am very annoyed by it. But it's tiny and it's not relevant to our conversation. So the only difference you need to remember is that counter zero is not actually used to encrypt plain text. It's used to do the authentication stuff. Cool. But still, some of it is going to be nonce, some of it's going to be counter. In GCM, the first 96 of the 128 bits is nonce, and the latter 32 bits is counter. So the first thing that we learn from this is that how many blocks can I encrypt at most in a single message? -1, because the first one I need for authentication. And 2 to the 32 times how big is the block? Big, exactly. Big. That's not a big number. So at most, we can encrypt 64 gigabytes, well, technically minus 120 bits, in a single message before the counter runs out and we have to stop with the message. So GCM will encrypt messages that are most that large. But there is another issue with size here. The 96 bits, how do we make sure we never reuse the nonce? An easy way is we pick it at random, right? That way we don't have to keep track of which ones we've already used, because maybe we're using the same key on multiple machines and they can't coordinate to be like, okay, I'm going to use 1, okay, I'm going to use 2, 3, and 4, okay, I'm going to use 5. They would have to talk to each other, and that's a distributed systems problem. Distributed systems are hard. So instead, they can maybe select things at random. How many can we encrypt before we have a problem?
Birthday problem.
It's the birthday problem. It's always the damn birthday problem. So a quick way to calculate the birthday bound is that we generally want the attacker advantage to be at most 2 to the minus 32. And a quick way to calculate the number, how many draws we can do before we can expect a collision with probability 2 to the minus 32 is that you take the space, which is 96, for example, you subtract 32, which is your intended bound, and then you divide by 2, because every time there's a birthday attack in the mix, it's going to be the square root of the number of tries or the amount of work. So that means we can encrypt at most 2 to the 32 messages before we have a problem. 2 to the 32 messages, that is not a lot of messages. I know that looks big, 4 billion. There are definitely systems that need to encrypt more than 4 billion messages. And these are generally annoying things. There are a few solutions. Can you think of a solution? You have enough tools from yesterday and today to think of, to couple one together.
Is it apart from making everything bigger so the numbers go up?
So the one thing we can't make easily bigger is the cipher, because AES, even if AES has the 3 key sizes, but all 3 key sizes have the same block size, 128 bits. NIST is talking about standardizing Regindel 256, which would be the 256-bit cipher, but that's just not existing at this point. So that is the one thing we can't make bigger.
Maybe change the key.
The important thing is that we need to not reuse the same nonce with the same key. It's fine if the nonce is the same, but the key is different. And we know how to derive keys, right? We have a key derivation function from yesterday. So instead, what we can do is we can take a large key, 256 bits or 128 bits, doesn't matter. We take a larger nonce, and then we do a key derivation of key and larger nonce. And from that key derivation, we derive 2 things. We derive a fresh key for every message, and we derive the whole nonce for every message. Now it's 224 bits of random space. So how many messages can we encrypt before an unacceptable risk of collisions? A lot of messages. We're not going to encrypt 296 messages. Don't worry, not happening. And this is generally how a lot of higher level designs are done these days. They do key derivation on larger nonce and key, and then from that they derive both the key and the nonce to use with GCM, and every message gets a fresh pair of key and nonce. That way you expand your space to not just the nonce, but to nonce and key. And that gives you a much better bound, both against birthday attacks and against multi-target attacks. This is from the first lesson we talked about. Birthday attacks are, birthday bounds are a problem. But it's also a problem if the attacker can say, look, I want to break one of these 2 to the 64 messages. I'm fine with breaking even a single one of them. So I'm going to try keys and check if I get the right hit until I get a hit across 2 to the 64 messages. And with that, 128 bits of key can be too small. So you also want the nonce to be random. And if only the nonce is random, then you're back in the multi-target problem. So instead, with 224 bits, you have space forever. So yeah, these are generally most modern designs you will find have that shape, but we're talking very modern, like things from the last 5-10 years. TLS 1.3 does that. TLS 1.3 derives the entire thing from derives both key and nodes from the key derivation function. Cool. One more statistical thing we need to worry about. So this one is a little annoying because remember our target for games from the first lesson. We want encrypted messages to be indistinguishable from random. Why do we want them to be indistinguishable from random? Because that is a lower bound on the confidentiality security as well. If you can't distinguish something from random, you're not extracting any information from it, which means you can't decrypt it. If you had any attack that extracts some bits of information from something, you also have a distinguishing attack because that you can just run your confidentiality attack and use the bits you learn to tell, oh yeah, that one is encrypted because I've learned something from it. That one is not because I can't learn anything from it. So in that sense, it's useful to analyze the indistinguishability bound of something because it gives you a lower bound for the confidentiality bound of something, which is something that generally we want to tackle. Now, there is a little problem with CTR. And it's that, remember that this is not a PRF. This is not a function that taken an input, returns a random output from it. Why? Because these will never collide, which sounds like a good thing. Not necessarily. Why do they never collide? Because the decryption function exists, right? So every input in AES has one output, and every output has one corresponding input. AES is bijective. Because again, you can encrypt and then decrypt quickly. So you have to be able to go back and forth. So everything has a one-to-one map. If you encrypt enough blocks, you eventually are able to tell that you're using AES and not, or another secure block cipher, and not just generating random bytes. Because if you were just generating random bytes, you would expect 2 blocks of keystream to at some point collide. So the distinguishing attack here is I ask you to encrypt zeros and just keep encrypting zeros, like a giant message of all zeros. And I check if any 128-bit block appears twice. Eventually, because of the birthday bound, you would expect that to happen, right? We can even calculate after how long we would expect that to happen, which is square root. But when it doesn't happen, we have a distinguishing attack. So if we observe enough blocks of CTR, we can distinguish it from random. But we don't learn anything else, right? We've only learned, well, great, it's encrypted. I probably already knew that. Thank you very much. Like I didn't actually think this was random bytes. I didn't actually think that computers were just shouting random bytes at each other. I already knew that these were encrypted bytes. So these are annoying in the sense that they are useful theoretical tools because if you can prove an indistinguishability bound, you've proven a security bound that you care about. When you break an indistinguishability bound, then there's a bunch of hand-wringing about, well, but does it actually matter? Because I would very much like to encrypt that many blocks, and can you show an attack? It took forever to get an actual attack that uses that. There's a paper about the missing difference problem, which uses sieving, and I'll be honest, I cannot explain it to you. I still have to read that paper at least another couple times before I have a fully formed intuition. And a lot of the field did not have an intuition for how to actually do an attack on CTR based on the fact that AES is a PRP, a permutation where it has no collisions instead of a PRF. This is called the PRP-PRF switching lemma, like the theoretical tool you use to analyze how using a PRP affects it. And it's just very annoying because it also compounds the distinguishing attacks across messaging. Because if you encrypt, usually we say that you want to encrypt at most 2 to the 42 blocks before the attacker has a strong chance of figuring out detecting that you are not random. Why 2 to the 42? 128, which is the block size, minus 32, which is the intended 48. At that point, it has a 50% chance of up to the minus 32 chance of succeeding. 48 or 42? 48, yes. So you want to stay away from that limit, from that number of blocks. If you do it once, you're fine. But if you encrypt many messages of that size, now the attacker's chance of succeeding compounds, because they are going to check whether the first message has a duplicate in it, and no. Second message has a duplicate in it, no. Third message has a duplicate in it, no. Fourth message, if they keep getting no's, they get more and more confident that those are not random, but encrypted. Again, this is a distinguishing attack, and I don't actually know if there is a confidentiality attack that works across keys. This is literally something we're discussing in a Slack conversation with a person who does theoretical analysis, because we need it for actual design, which I'm working on, which is this. Maybe. And it does that by chunking the message and encrypting each chunk with GCM. So there's a lot of chunking going on. Each chunk gets encrypted with GCM, and then GCM breaks them into blocks to encrypt with the thing. And this is a way to encrypt things that are larger than those 64 gigabytes, because remember that GCM has this limit over here of how many bytes you can encrypt. And there are things bigger than 64 gigabytes, right? So generally, we need a scheme to encrypt something bigger than that. And you would think that we had the standard one. And we don't, because cryptographers like to design fancy things, and the simple things, they're like, well, you can just, encrypt them all with a counter nonce and GCM, it's fine. And that means that then the implementations are not reusable, and then people get it wrong in all sorts of ways. And I have so many opinions on the fact that we have not standardized chunked encryption. Also, very annoyingly, the best design that was analyzed until recently was called Stream, which is the worst possible name, because I just taught you about stream ciphers, right? And the stream ciphers are the unauthenticated block-based ones. And then from a stream cipher, you make GCM. Well, from CTR, you make a stream cipher. From stream cipher, you make GCM, which is a authenticated encryption. Usually, you will see those mentioned as AEADs, authenticated encryption with additional data. Additional data is just because sometimes you want to authenticate not just the ciphertext, but also some extra information about it. But don't worry about it too much. And then from a AEAD, you can chunk it and make stream. That's what we're going to call it? Again, stream? And then when people ask us, oh, how do I encrypt something large? Oh, use stream. And then they Google stream encryption. They find a stream cipher, which is not authenticated. They use that. And then everything breaks because it's not authenticated. And you can do all of the Oracle attacks from before. I have opinions about our profession at times. Anyway, I'm working on the specification, and we're trying to figure out how much we care about those indistinguishability bounds and so on. So we very much hit the state-of-the-art boundary at this point. Like past this, I can't teach you definitive answers because we are discussing them basically at conferences right now. I wonder if I've skipped anything. No. Questions? So one thing that helps with thinking about the bounds forced by the block size is that there are older what? That's not it. Oh, it was with 32. Okay. So older block ciphers, DES, the predecessor to AES, had a smaller even block size. It was 64 bits. And turns out that that makes the bound before you can do attacks tiny. Because 128 already has an uncomfortable birthday bound after a few couple petabytes. But petabytes are kind of annoying to store. You can, but 64 bits now you can run on a laptop. So this is a nice attack to read. Like reading this paper, I think, is the easiest way to get an intuition for the actual attacks that you can do. I'm gonna put this in the notes doc, which, by the way, if you haven't scanned yet, notes doc. And of course, it will be in the recording. But go ahead. Right. So Sweet 32 is the attack against the smaller block size ones. We generally don't use 64-bit ciphers anymore, so not as much of a concern, but still. There are two schemes that you can check out for doing the derive both a key and a nonce to expand the nonce size trick we discussed earlier. The one where you can't take random 96-bit nonces because that would mean after 4 billion messages, you're out of margin. And one is for Chacha, and it's called X Chacha 20 poly 1305. The X meaning that the first thing it does is it uses that same permutation of Chacha to put together a key, half of the nonce. It runs it, it derives a new 256-bit key, and then uses the other half of the nonce with the actual block cipher. And that way it extends it. So remember that Chacha looks like is the thing that makes a stream cipher by just permuting this state. How it does it, how X Chacha works is that it puts some other stuff at the top, like a different constant at the top. It puts the main key, the one that doesn't change between messages here. Then it puts half of the main nonce here, which means that this space is 32, 64, 128 bits. Runs the thing, and running it, it gets out a new key. So it runs the permutation, it takes 256 bits of the output and says, good, this is the key for this message. And then that means the nonce space is the nonce space of the actual operations you do to do the encryption, plus the one you put in to derive the fresh key. So the result is that it has 196 bits of nonce space. And then there's a design called XAES, which I put together, I don't know, 2 years ago, which does the same thing for AES GCN. It's pretty much the same thing. It's boring. The only clever thing it does is that it has a story for why this is FIPS compliant. Like it has a story for why this is follows the NIST regulations, so that you don't have to convince to it. The problem with designing anything new at the low level is that it will probably not be compliant with national standards. And so you have to use the approved tools, which sometimes they are not as nice because, for example, they have a small nonce space, which means you can't encrypt many messages before you have a problem. What this does is that it goes like, well, you do these operations here, and you can just consider them like that. But if you squint, actually, these 3 steps can be also described as using a NIST-compliant key derivation function between the key and a nonce to derive a fresh key. And yeah, it's contortions that are not security relevant. They're just there so that people that have to follow national regulations can use this, and we don't have to make one thing for when you require compliance and one thing for when you don't. Anyway, I can post this in the notes, but I think XChacha is probably more interesting to look at because it's a little cleaner and more intuitive. But they do the same thing. Just that one is optimized to use Chacha, and this one is optimized to use AES to derive the key. How it does it is that this part is you can basically ignore. It derives the new key here by XORing a fixed message plus the first half of the large nonce with the key. It encrypts them both, and that's how it gets the new fresh key, the per message key. Does this make sense? Like the thing that we have a main key, which is fixed across messages, and we use it to derive a per message key so that we don't risk reusing a key and nonce pair with 2 different messages. Does that make sense? Like how we derive it exactly doesn't matter. The intuition is just to avoid the perfect collisions, we derive a random key and nonce every time so that the pair does not collide. Make sense? Cool. If you don't have questions, I think